Hi friends, welcome to Follow Up. Let's have a look at problem 1930, unique length 3 palindromic subsequences. In this video, we're going to share two formats of solutions. The first one is based on dictionary, so we are going to focus on the middle character. Well, for the second one, we are going to use index and the right index, and we are focusing on the two ends. With that said, we are going to do the following plan. First, we are going to digest the problem requirements, and then we do the analysis and share the code. So now let's look at the problem digest. So here we are given a string s. We want to return the number of unique palindromes of length 3 that are a subsequence of s. So here the word unique is very important, right? So a palindrome is a string that reads the same forwards and backwards. I guess this is very familiar to us. So there are three examples. In the first example, the output is 3. So if you look at A, so you see A first appears at index 0 and then at index 4. And in between, there are 3 different characters, A, B, C. So we return 3. If you check B and C, they both appear just once. Therefore, there are no palindromes of length 3 and ending with B or C, right? In the second example, all the characters are unique characters. Therefore, the output is 0. Now, similarly, you can examine example 3. So here, B first appeared at index 0 and then at index say 1, 2, 3, 4, 5, right? In between, there are 3 unique characters, A, B, C. So the order are B, C, A, right? Anyway, this B, in other words, there are 3 unique palindromes ending at B. So if we look at A, so we have A, B, A, right? There's 1 palindrome ending at A. So in total, we are going to get 4, right? That's the return. So with that said, you can also quickly look at these constraints. So now let's look at our analysis. So in the first solution, we're going to focus in on the middle character. So and then we check the two ends characters. So here we want to use this one. So S consists of only lowercase English letters. So we know that there are 26 lowercase English letters, right? So this actually simplifies the problem in a sense. So first, I'm going to, from string, import ASCII lowercase. So this import helps us to avoid writing the A up to Z strings, right? And then our goal is to linear scan this string S. So we're going to look at the left of the current index and the right of the current index. And then we check every lowercase letters. So first, I'm going to use this 3 dot as a set. So this is going to deduplicate, right? This is the result. Left is a dictionary. This is a set. So corresponding to the number of unique characters to the left of the current index, you can think like this. The right, because originally we haven't do the linear scan. So the right, we can regard everything is on the left. So let's use collections counter S. So now let's do the linear scan. So for I in range length S. Then because we are currently looking at the character SI, so we need we can begin to put things to the left. So what we think is that left is going to add SI for next round, right? So now let's look at the current situation. What we want to do is the right, because currently we are looking at the current is decremented by 1, right? So then we want to check if right SI is 0, right? So we just need to delete this K, right? SI. And then the main logic is that, so we use the current character SI as the middle character, and then we check the two ends to see if there are some characters they provide the same. They both appear in left and the right. So notice that there's a sort of asymmetry. So left we are using a set, and the right we are using a counter. So the reason is that we need to make sure after certain index, so if there are occurrences of certain letters. So now let's do the check. So for character in ASCII lowercase, so then we just do a check if character in left, so that's the one, and if character add character in right. So if this is the case, so actually we know we have a palindrome that is character SI and character. But due to the fact that the left and the right are the same, so we can map this or make correspondence or hash it like SI and the character, right? This is the same. So we use this to represent a length 3 palindrome. So basically it says the middle character is SI and the two ends has character. So we append this, we are append a tuple. This is hashable, right? That's the basic logic, right? So afterwards, so we just do this. Yeah, if you look at the next round, basically, because we have finished the looking at the current index or use it as a middle character, then SI will appear to the left, right? Then that's the state of the left set, right? So now what we want to do is just to return the length of this result. So here, because we want to return unique palindromes, so this set plays the role of deduplication, right? So this actually forms one solution format. We can do a test. Set has no attribute append. So here, let's see. Let's use add. So now let's do it again. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes the generic cases. So now let's look at the second one. So notice that in the first one, in a sense, we are focusing on the middle character, right? So we use SI as the middle character, and then we check all the different ASCII lower cases. So this solution actually take advantage of the second constraint, that is S consists of lower English letters only. So now let's look at the second solution. For the second solution, we are going to look at or focus on the two ends, right? So for this actually is similar to, let's use example 1 to recap. So here I check the index for A. So A first appears at index 0, and then A appears at the rightmost index, that is 4, right? 1, 2, 3, 4. And in between we have A, B, C. So this contributes 3 different palindromes ending at A. So actually, in order to check, for example, in example 1, the palindromes ending with 2 characters A. So we just need to look at the first occurrence of this A and the last occurrence. Why? Because in between it contains all the possibilities. So this, why we check the first and the last. Actually, this is due to the assumption that we want to find the number of unique palindromes. So because this, so we just need to, for any character, if we want to check the palindromes ending at that character, we just need to check the 2 indices, the first occurrence and the last occurrence of that character. So this, then we check the middle. So to retrieve the different characters, this will include all the possibilities. So if you have grasped this simple idea, and then the coding is very simple. So here basically, let's use the characters. This is a different or unique characters in S. So here, if I write like this, we didn't take specifically use this lowercase letters assumption. So actually, even it appears there's other characters in S, this still works. So let me initialize a result variable. This is the counting variable, right? Then we are going to check for character in characters. So we want to use this character as the ends of palindromes, right? So then we want to check ij. So this is s index character, and then s r index. So character. So this r index will be the rightmost index. You can understand like this, right? So now the between we want to see now that we know this, so it's possible that I and j are the same, but if that's the case, they do not contribute anything, right? So now let's do this. So basically I want to write result increment by length of set of s I plus 1 to j. So in other words, I want to count the unique characters in between I and j, but both exclusive, right? So then we just need to return the result variable. So this is the second solution format. So I wrote like this because this saves some writing, but it uses the string slicing, which can be time consuming. So now with that aside, let's do a test. Yeah, it passes one special case. Now let's look at the generic case. Yeah, it passes all the generic cases. So I guess basically that's about it for this problem. So here in the first one, let's quickly look at the temp complexities, right? So we do this one. This is essentially linear operation, and then this is also linear. But in between we have this one. If you also count this for loop, but this for loop iterate each time 26 times, because ASCII lowercase is a constant bounded by a constant 26. This is the one. This is the temp complexity for the first version. For the second version, this is also essentially linear operation. And then here we have a for loop. These two are linear operation, but here the temp consumed is like we do the slicing. This can be time consuming. With that said, I guess that's about it for this specific video. You're welcome to follow up our videos or channels. So there are some other types of problem that can be practiced. With that said, I guess that's it.